My esteemed listeners, this tutorial presents the space and time trade-off strategy of algorithm design. Space and time trade-offs in algorithm design are a well-known issue for both theoreticians and practitioners of computing. Consider, as an example, the problem of computing values of a function at many points in its domain. It is, if the time is at premium, we can pre-compute the function's values and store them in a table. This is exactly what human beings or human computers had to do before the advent of electronic computers. In the process of burdening libraries with thick volumes of mathematical tables, though such tables have lost much of their glitter with the widespread use of electronic computers, the underlying idea has proven to be quite useful in the development of several important algorithms for other problems. In somewhat more general terms, the idea is all about pre-processing the problem's input in either in whole or in part, and store the additional information about the input in a table only to accelerate the solving of the problem afterwards. We call this approach to be input enhancement. Simply told, in this strategy, we trade off the space in order to save the time, or we trade off the time in order to save the space. Of course, latter need not be done with the computer space or computer memory available at a very cheaper rate. Therefore, we conjecture that this discussion or this strategy reduces to space trade-off. There are two versions for this algorithm design strategy. One, the input enhancement. In this version, the idea is to pre-process the problem's input in whole or part and store the additional information in a table. It is additional information about the input. It's very important to remember the fact that the additional information that we glean, it is from the input itself. And we will use this information, additional information, maybe enhanced information about the input to accelerate the solution process. Therefore, we make the algorithms time efficient. That's what which is needed. All of you will understand, will definitely accept that is what which is needed. And we have three examples over here. One, counting methods for sorting, Horspool's algorithm for string matching, and Boyer-Moore's algorithm for string matching. And the second approach is, the second version of time-space trade-off is using extra space to facilitate the faster access to the data, say in a database management system. For example, considering constructing a different table in order to store the keys, so that the access to the keys should happen at a much faster rate. If keys are found, the information about that particular record is also found. And the other one is B trees. Okay, it comes like pre-structuring, wherein it will facilitate a quicker access to the data. And in this tutorial, we consider elaborately the first example of the first version, that is input enhancement. And this comes as a sorting method, and it is named as sorting by counting. Here you consider this array which is not sorted, and the method is sorting by counting. Here in this method every element is considered, and we will literally count as to how many elements are lesser than this. For example, 87 is the first element, and we will just count from the second element onwards as to how many elements are lesser than this. For example, in this example, 51, 39 and 67, they are lesser than, and 83, they are lesser than 87. Therefore, there are 4 elements which are lesser than 87. Therefore, in this sorted array, 87 should find its pride of place to be cell number 4. See, in the same token, if you consider 51, the second element, okay, the number of elements which are lesser than 51 are 39 only. Therefore, there is only one element which is lesser than 51. Therefore, 51 should find cell number 1 in the sorted array. As far as 104 is concerned, there is 87, 51, 2, 3, 4, 5. There are 5 elements which are lesser than 104. Therefore, 104 should find the cell number 5 in the sorted array. Similarly, for 116. Okay, 116, all other elements are lesser than this. There are 6 elements which are lesser than 116. Therefore, 116 should find the 6th position in the sorted array. That is the last position. Okay, if the things are arranged in ascending order. Similarly, the iteration will go up to the point of up to the element 83, and every element will get how many elements? A count of every element will get a count of how many elements are lesser than that particular element. Okay, and I will illustrate the working of the algorithm, the implementation of the algorithm, rather how it works, by taking this particular specific example. Okay, first of all, we need to generate an array called as count array. This count array holds the counts against each and every element, the count being as to how many elements are lesser than each of the elements. So count is initialized to 0 because there is nothing to gather. Okay, so all the elements, all the 7 elements will be initiated to 0. Then in the first iteration, a count of number of elements lesser than 87 is made. Okay, this is lesser than. Okay, the counting will start from the next element. So 51 is lesser than that, so it will get 1. 104 is greater than 87. Therefore, 104 will get 1 to its account. 116 is greater than 87. Therefore, this will get 1. 39 is lesser than 87. Therefore, 87 will get 2. 1 is already there, it becomes 2. Then 67 is also lesser than 87, it will become 3. And 83 is also lesser than 87, this will become 4. So in the first iteration itself, the first element will get a count of how many elements are lesser than 87, or how many elements are lesser than the first element. Okay, therefore the first element need not be considered again in the second iteration. So in the second iteration, we will make a count of how many elements are lesser than 51. Okay, for that we will start from 104. Okay, 104 is greater than 51. Therefore, 104 will be incremented. It will get another account. Okay, it will become 2. Okay, because 104 has 2 elements lesser than that. Therefore, it will get the account. Okay, account enhanced. And 116 also will get 2. 39 is lesser than 51. Therefore, 51 will get 1. And 67 is greater than 51. Therefore, this will get 1. And 83 is greater than 51. Therefore, this will get 1. Okay. Then in the next cycle, this can also be avoided. Okay. So 87 has got 4 elements lesser than 87, and this element has got only 1 element lesser than 57. And we will, if you start with 104, okay, 116 is greater than 104. Therefore, this will become 3. 39 is lesser than this. It was already 2, so it becomes 3. And 67, 4, 83, 5. Okay, 83, 5. And now this can be avoided. Now, so comparison, the counting will start for 106. It has already gathered 3 elements being lesser than this. Then 39 will be compared with 116. This is lesser than 116. Therefore, 3 plus 1, 4. 67 is lesser than 116. It becomes 4. It becomes 5. And 83 is also less than 116. It becomes 6. And there is no account increase for 39 or 67 and 83 because they are lesser than 116. Therefore, this can be eliminated from counting. Okay. Next, 39 will be compared with other elements, and it has no other element lesser than that. Therefore, there are 0 elements lesser than that. So it will get 0 to its account. Then 67, we will start comparing 67 with the other element. It has already become 2, okay, because 39 is lesser than 67 and 51 is lesser than 67. Okay, when we were at 39, okay, it got an account increased, and when we were at 51, it has also got its account increased, therefore it has become already 2. Therefore it need not be considered again in the third cycle. Okay, therefore it has become 2. Now 83 will already have got its account to be 3. Okay, when we start comparing 67 with 83, 83 got its account increased rather than 67. Right. Now count array, by the end of n-1 cycles, the count array will be filled with the respective positions of all the elements of the original array in the sorted array. That means 87 has to go to the 4th position in the sorted array, 51 should go to the 1st position in the sorted array. Okay, so this is the sorted array actually. So 87 has to go to the 4th place, then 51 has to go to the 1st place, okay, and then 104 should go to the 5th place, and 116 should go to the 6th place, and 39 should occupy the 0th place, and 67 should occupy the 2nd cell, and 83 should occupy the 3rd cell. This is how by consuming extra space, of course we had extra space, you can recall from the explanation that is being done, we need a separate array for count array, we need separate array for sorted array, and in between also we had many arrays, many empty arrays. Therefore we have used extra space in order to save the time. So as far as sorting is concerned, it is simply placing the original elements in the unsorted array in the positions shown by the count array. Okay, so I think the things are understood, and we will just right away barge into writing the algorithm. Comparison count sort. Okay, A0 to n-1. What it does, it sorts an array by comparing comparison counting, input an unsorted array 0 to n-1, and output a sorted array S, which is an extra space, of course, of A's elements on ascending order. Okay, for I equal to 0 to n-1, because it needs n-1 iterations. Okay, the last fellow need not be compared, because there will be nothing to compare for the last element. It will gather its counts. Okay, n-1 iterations. Okay, that means n-1 times n-1 elements are to be sent, okay, iteratively for the comparison. Okay, n-1 iterations, and every iteration, okay, so this is for initializing. Of course it is not for the iterations, it is for the initializing the count array. Okay, the count array is initialized with zeros because it has nothing in store. It has to gather, it has to accumulate. So here exactly the algorithm starts. Okay, we start the algorithm by writing the iterations from 0 to n-2, because n-1 iterations are needed. Since we use the word 2, we have to go up to n-2, because lesser than n-1 is nothing but up to n-2. Now the second array, the second for loop, the inner for loop, is for comparison. Okay, when 0th element is let for comparison, of course when 0th element is sent for comparison, the comparison should start from the next element. Therefore it will start from I+1 in every iteration. Okay, and it should go to the last element. Okay, the comparison should be carried up to the last element. Therefore it will start from I+1, it will go up to n-1. Okay, this is exclusively for comparisons. Okay, now if A of I, let us say in the first iteration, if A of 0 is greater than A of j, then the account for the ith element should increase. Therefore count of I will become count of I+1. Okay, on the other hand, if A of I is less than the other element, okay, then the other element's count should increase. Okay, the other elements count should increase, because this element is being lesser than this particular element. Therefore this should receive, the other element should receive a increased value as far as count is concerned, because this will be accommodated as an element which is lesser than the other element. Now we have all the elements in the count array being filled. It is nothing but the respective positions of the elements of the original array in the sorted array. I repeat, count array contains the positions of the respective elements in the unsorted array or original array in the sorted array. Therefore the thing is very simple. So here exactly, I should say, here exactly sorting will take place. Yes, the sorted array, okay, the elemental position in the sorted array available from the count array, okay, which was 4 actually in the given example. It was 4. Yeah, that is the thing. I think things are very clear to you, viewers, right? S of count, that is the number of counts available for the first element should become. So here what goes is S of 4 is equal to A of 0. S of 4 is equal to A of 0. That 4 comes from count array. The fourth position is shown to, the fourth position in the sorted array is shown to the first element in the unsorted array. That's how it goes. Okay, we will literally fill up the elements from the original array into the places that is being shown by count array, because count array will contain a count of number of elements which are less than this particular element. Okay, as far as the complexity is concerned, the comparison is the basic operation that happens in the initial steps of the algorithm. Therefore the number of comparisons as a function of n input size is there is only one comparison which goes from j equal to I plus 1 to n minus 1, and this is I equal to 0 to n minus 2. Okay, now upon simplifying, we will reduce, this expression will be reduced to n into n minus 1 divided by 2. Therefore comparison counting sorting belongs to big theta of n square only in terms of comparisons, only by spending the extra space. Of course sorting happened immediately because we just placed elements from the original array into the positions that are shown by the count array. Okay, and these positions happen to be the positions of this original elements in the sorted array. Okay, there are two important questions that are to be answered. Is it possible to exchange two values, say u and v, without using extra storage? Yes, it is. With a little modification we can always write, we need not have to use extra space. Let us say it will be through very simple expressions, arithmetic expressions. Let us say u will be made u plus v. Okay, that means u holds u plus v, v holds v only. Okay, v holds whatever the value that was originally contained. V now can be said as u minus v. If you do that, u holds u plus v still and v holds u. Once again we will once again say u minus v. Okay, now u holds v holds u, and we will take a typical example, okay, to illustrate this. Let us say u equal to 7, v equal to 8. Okay, when we say u equal to u plus v, it becomes 15. When we say v equal to u minus v, it becomes 15 minus 7. It becomes 8. So v becomes 8. Sorry, v becomes 7. Sorry, v becomes 7. Because v holds 8, u holds 15. 15 minus 8 is 7. And u still holds u plus v, that is 15. And u minus v, v has become 7 now. V has become 7 now in this particular step. Therefore, u will receive 15 minus 7, that is 8. So without using extra space, it is possible to exchange. Okay, it is possible to exchange the values. Will the comparison counting algorithm works correctly for arrays with equal values? Yes, it is. It's an emphatic yes, because whenever we start counting, the next element is not lesser than the element that is being considered, and also the next element, like this. It won't get a count. It is equal to, and even the other element will also not get a count, because it is equal to this element. Therefore, the elements remain in their respective places. So with this, we can conclude this particular session. In this session, we took an example of input enhancement. The input was a unsorted array. It was enhanced in terms of building a table which contained which is called as a count table or count array, which contained the positional value of each and every element in the unsorted array, okay, in the sorted array. Okay, they are nothing but counts of number of elements which are lesser than each and every element. Okay, if 4 elements are lesser than the particular element considered, then that element is to be posted to the 4th position. Simply told, this is the meaning, and this is exactly how the comparison counting algorithm worked. Anyway, it used extra space as we have promised. We made a trade-off of the space in order to reduce the extraordinary time it would have taken in order to sort, because you will still agree with me, sorting will always involve number of comparisons.